Example 3. A balanced three-phase load requires 480 kilowatts at a lagging power factor of 0.8. The load is fed from a line having an impedance of 0.005 plus J 0.025 ohms per phase. The line voltage at the terminals of the load is 600 volts. Part A, calculate the single-phase equivalent circuit of the system. Part B, calculate the magnitude of the line current. Part C, calculate the magnitude of the line voltage at the sending end of the line. Part D, calculate the power factor at the sending end of the line. So the first thing we are going to do is we're going to draw the equivalent circuit, which is part A. So what we're going to have here is at the sending end of the line, we're going to have A and the neutral and represent the voltage between them as VAN. And then we're going to have the line impedance, which is going to be a resistor with 0.005 ohms and an inductor with J 0.025 ohms. And then over here, we're going to have node A, capital A, and down here, we're going to have node capital N. And then the load is in between A and N. And that load is going to be 160 kilowatts. Because remember, this is 480 kilowatts, but it's only for one phase. So we take that value and divide it by 3. And the lagging power factor is still 0.8 lag. And we represent the voltage across here as V capital A capital N. But it's the voltage for only one phase. So that voltage should be 600 divided by the square root of 3. With an angle of 0 degrees. And remember, I'm getting these formulas from all of those formulas we presented at the beginning of this lecture. So then our relationships are V line equals the square root of 3 times V phase. And therefore, VAN would be equal to VAB divided by the square root of 3. And that's where we get the 600 over the square root of 3. With an angle of 0 degrees in volts. The total power, recall, is going to be 3 times the phase power. And the phase power then would be 480 kilowatts divided by 3, which is where we get the 160 kilowatts from. For part B, we're going to calculate the magnitude of the line current. In order to calculate the magnitude of the line current, we need to find the total complex power. So first, we're going to find Q. So note that we have a power triangle here, where this would be S, P, and Q. And what we have so far is that P is 160 kilowatts. And the power factor angle would be equal to the arc cosine of 0.8. So that angle is equal to 36.87 degrees. That means this angle here is 36.87 degrees. So if I want to find Q, Q is equal to 160K times the tangent of 36.87 degrees, which equals 120 kVAR. So that means that our complex power would be S equals V phase I phase conjugate. And that would also be equal to, in rectangular form, 160 plus J120 kVA. So that's for one phase. So that means if I want to find the line current, which is equal to IA, lowercase a, then that's going to be equal to S over V phi conjugate. So that equals 160 plus J, 120K, divided by 600 over the square root of 3 conjugate. And we get that that current is equal to 577.35 with an angle of negative 36.87 degrees. And the units are amps. Part C is to calculate the magnitude of the line voltage at the sending end of the line. So this is part C. And so that formula is going to be V lowercase a lowercase n equals the voltage drop across the line, which is Z line times IAA, plus the voltage at the load end, which is V lowercase capital A capital N. So this is going to be equal to 0.005 plus J 0.025 times the impedance of the line times the current, which is 577.35 with an angle of negative 36.87 degrees, plus 600 over the square root of 3. And we get that VAN is equal to 357.51 with an angle of 1.57 degrees, and the units are volts. So that's our phase voltage. So now if we want our line voltage is equal to VL times the square root of 3. And this is only the magnitude, so it's going to be times the magnitude of VAN. So that's going to be the square root of 3 times 357.51. So the magnitude of VL is equal to 619.23 volts. Finally, our last step is to calculate the power factor at the sending end of the line. So the power factor is going to be equal to the cosine of theta VAN minus theta IAA, which is the cosine of 1.57 degrees minus negative 36.87 degrees, which equals the cosine of 38.44 degrees. That angle is greater than 0, so it's going to be lagging. And so the power factor is 0.783 lag.